RETScreen Expert, Tips and Tricks for Climate and Weather Data, presented by David Elfstrom. Welcome to my series of videos sharing how I use RETScreen Expert software from Natural Resources Canada. In this video, I'll be going over the climate and weather data used by RETScreen for its energy models. First, I'll talk about the climate data location as compared to the facility location. Then we'll look at two sources of climate data you'll see in RETScreen: ground data and NASA satellite data. We'll look at where the design temperatures are sourced from, along with a caveat in their use. Then I'll show you where the satellite data comes from and how you can use it to create custom climate entries for remote locations. Finally, we'll download some recent weather data in the Performance module and use it to improve our energy model's prediction. RETScreen is built to be quick and easy to use, getting you close enough to the right answer as long as your inputs are reasonable. In nearly all cases, you'll be fine using the climate and weather data without any concern. But it helps to understand the differences between climate and weather, where the RETScreen values come from, and how to make changes when needed. Starting on the Location tab, we have two main inputs. One for the climate data location, represented by a globe, and one for the facility location, represented by a house. The climate data location has long-term averages used by RETScreen in its many energy models. The facility location is used for daily weather data directly at that location in the Performance Analysis module of RETScreen. When we open the database, we see a map with a series of points, each representing a location containing long-term average climate data. Red circles are climate locations that utilize long-term, on-the-ground or on the water measurements. In total, there are over 6,000 sites in RETScreen Expert using data compiled from over 50 different sources. Blue circles are climate locations with long-term data derived directly from NASA satellite data. As I drag my facility location marker around the map, you'll notice the climate data marker is snapping to the nearest climate point. If I'm only doing a performance analysis using weather data, the climate data doesn't matter. But if I have an energy model, standalone or with the performance data specific to the facility, then I will need to consider my climate data location. On the map, the climate data can only be selected for one of the red or blue points. Let's look at a few different examples. Select an area near a blue dot and you can click View Data. Let's look at Owen Sound. Here we see all the data sources. Every single one are all from NASA satellite data. Let's look at another location. Here's Huntsville. Same thing. Now let's look at one of the red markers with ground level measurements. Ottawa International Airport has most data from ground stations, with only Earth temperature amplitude, precipitation, and Earth temperature monthly supplied by NASA. Toronto International Airport is similar, but atmospheric pressure is also sourced from NASA. Elora is almost entirely NASA satellite data. Only the elevation and the daily solar radiation is sourced from the ground data. Our choice of which data to use would depend on our intended use. If we were going to do a pre-feasibility screening for a potential solar project near Elora, we would want to select that data. But if I'm looking at a building energy model located near Elora, I should consider Guelph instead because it has ground data for air temperature. While we're here, let's take a quick look at the design temperature fields. Guelph has a heating design temperature of -19 Celsius. Switching back to Elora, it has a design temperature of only 11.6 degrees, using NASA satellite data. That's a huge difference, and not realistic based on the proximity of the two locations. Design temperatures are based on local extremes and the satellite data is not great at detecting those. Design temperatures are primarily used by engineers when selecting heating and cooling equipment to ensure it has enough capacity in the coldest for heating design or hottest for cooling design days of the year. RETScreen uses the design temperature values in its models for individual systems, such as biomass heating system, for example. The design temperatures in RETScreen, when sourced from ground-based instruments, are mostly the long-term annual 1% hourly values. 1% of a year is about 87 hours, so we can expect that 87 hours a year, the temperature will be below this design value for heating, or for a cooling system, the air temperature can exceed the cooling design temperature 87 hours a year. It probably won't happen all at once. It might be spread out over a few hours each day for a week. Many of the values in RETScreen come from the ASHRAE Fundamentals Handbook. Let's look at Atlanta, Georgia, in the United States. The heating design temperature is minus 3.5 degrees Celsius, and the cooling design temperature is 33 degrees Celsius. Here are the design conditions in the 2009 edition of the ASHRAE Fundamentals Handbook. We see the heating design temperature is from here, minus 3.5, and we see this is also where the cooling temperature comes from, at 33 degrees. But there are many other design temperatures here, such as the 99.6% temperature, corresponding to about 35 hours a year. And cooling is split into many different conditions, including humidity, for equipment like cooling towers that use evaporation, or other systems that dehumidify. Oh, one important note, RETScreen doesn't use latent heat when calculating cooling energy in its building energy models. It only uses dry bulb, not wet bulb. Also, ground values measured at an airport can be a little different than a nearby dense urban location. In short, RETScreen ground-based climate values for design temperatures are reasonable to use, but if you're modeling an individual heating or cooling measure and the climate data shows NASA for the design temperatures, caution is warranted and you should probably consider a different source. Alright, so where does this data come from? And what if I want to use NASA data at another location? It's all in the Power Data Access Viewer available through a web browser. The data here is from satellites, measured on a half-degree grid. Here's the grid, with lines on a full degree increment. You can imagine that each of these 1 degree regions is split into quarters. Each quarter of the grid in this area is approximately 40 kilometers wide by 50 kilometers tall. The dimensions change as you move around the globe. Clicking within this grid, we can see the 30-year climatology average for a particular point. Notice how it stays the same within the quadrant. As soon as we pass over a degree line, or one of these invisible half-degree lines, the value changes. Most of the data used by RETScreen can be found under the Sustainable Buildings group. We can get recent daily data used by RETScreen's performance module, recent monthly data, and long-term average climate used for the climate locations in RETScreen. Let's look at the climatology values and recreate those for Owen Sound. We need to select Owen Sound on the map. Next, we'll select some of the same fields that we see in RETScreen. The daily solar radiation is the same. The precipitation is in millimeters per day, so you have to multiply by the number of days in the month. For January, it's 1.74 millimeters per day, and multiplying by 31 days is 53.94, which matches the RETScreen value. The air temperature appears to be truncated rather than rounded. The heating and cooling degree days are very close, but just different. The NASA data is reported at 18.3 Celsius, while RETScreen uses 18. Since the daily data is downloadable back to 1983, I suspect the heating and cooling days were calculated by the RETScreen team using long-term historical data, and that they didn't use this 18.3 data, or even the 10 degrees data for cooling. And here's what that data looks like. The values in the climate section can be overwritten. So if you have a more remote location, you can enter values downloaded from the PowerWimp site by hand, or type in your own values if you have your own measurements. The energy models use the designated climate data. But when you are in the performance analysis section and downloading daily weather data, that daily data is for where you place the facility location, represented by the little house, not where you place the globe for the climate location. And it's going to be the same for any facility location within that 2,000 square kilometer grid quadrant. Okay, so what if we have an energy model for a building and we want to compare it to the actual bills for a particular year? Well, if the weather is a typical year and close to the long-term average, we don't have to worry. However, we know that we can have unusually mild or harsh temperatures for any given month. Let's look at our building in Owen Sound again. We can download the weather data covering the period of our bills, preferably a year, and then manually overwrite the climate data. Let's do that. Let's say we have energy bills covering the period of September 2015 to August 2016. So let's download all of 2015 to 2017. Now let's get our monthly data totals using the filter button. We should calculate the heating and cooling degree days as well. And these are the values that you can copy and paste into the climate data page. Let's have a quick look at these. Summing the heating degree days, we get 3790 and 1250 for the cooling degree days. On the climate data page, the long-term average is 4165 and 870 for cooling. If our model was focused on cooling, we would definitely need to overwrite the climate values in order to compare the model's prediction to the actual bills. And if you happen to have your own data, such as from a local weather station or a building automation system, you can import them into the weather file. I've done this for some weather stations using Environment Canada data, and the results are usually close enough to the NASA satellite data, although it does depend on the particular location. Dense urban areas or locations adjacent to large bodies of water can be quite different from that broad 2,000 square kilometer average from the satellite data. If you're doing a performance analysis and you're on the borderline for a regression measure of fit, you might want to try importing local daily weather data into RETScreen and repeating the analysis. Remember how the design temperatures from the satellite data weren't as severe as the ground-based design temperatures? The same applies for the daily data. The 2,000 square kilometer averaging can smooth out local extreme temperatures, so you can get different values for the minimum and maximum temperatures in the daily satellite data as compared to local weather station data. This especially applies if you're calculating degree days using the min-max method instead of the average temperature method. Typically, this is only used for when the shoulder seasons are of importance. Otherwise, using the average method for degree days is best. That's it for weather and climate data in RETScreen Expert. Remember, keep it as simple as possible. In nearly all cases, you should be just fine with the climate and weather data as it is. The most likely reason to adjust the standard climate data is when you are attempting to reconcile an energy model with a set of existing utility bills.